perihelion. I don't know. Is that how you say it? Perihelion. And aphelion. Aphelion? Aphelion. Anyways, they described the distance from the sun to a particular planet or whatever you might be talking about. I guess we could talk about anything that revolves around anything, where the thing that's revolving around would be the object that would make the path of the ellipse, and then it's revolving around the sun or the earth, the moon, whatever is at center. It's not really quite the center, it's the focus. So I guess if we try to graph this, we have a focus point, which would be in this case, the sun, and then the planet would be going around the sun. And then it's an ellipse, so it's elongated in one direction, and that elongation in that one direction is called the semi-major axis. And so there's a measurement of the shortest distance and the longest distance. The closest and farthest are called perihelion. This would be the shortest. And the farthest is the aphelion. And that total distance from end to end of the path is the semi-major axis. So with this information, we can try to, we could try to model the path of the Earth around the sun. We can try to model the path of the moon around the Earth if we knew the information that's required here, which is, looks like the distance, the semi-major axis, the distance, and the eccentricity. So, for example, if we're looking for A here, it looks like the perihelion distance is A times this, and the aphelion distance is this. So, if we work that out, that should just be A, right? If we add them together. Do we add them? Yeah, we add them. Is it A? Oh, it's 2A. Oh, sorry. So maybe this is 2A, the semi-major axis. Because if we add these two, right, A minus E times A, and then A plus E times A, the E times A would cancel, and then you just have 2A. So that looks like it's, that's what we're looking for, more or less. All right, well, we can, you want to try to find the path of the Earth, for example? We have to know the eccentricity of the Earth and stuff. And the distances, the farthest and shortest distance. So let's see if Wolfram can help us with that. So the eccentricity of the Earth's orbit looks like it's 0.016. So by the way, if it's equal to 1, remember that eccentricity is equal to 1, what do you have? parabola. And so if it's close to 1, like 0.9, you would expect this ellipse to be really elongated. And at some point, it becomes 1, eccentricity becomes 1, then it's just not going to loop back in itself. It's just going to be a parabola. Are you imagining this? And if it's close to 0, it's going to look a lot like a circle. And in fact, that's what people thought a long time ago, was that we thought that the Earth's orbit was circular, right? And then they just figured how far apart the planets were by, do you guys know about the platonic solids and stuff? Kind of embedded within each other. That they imagined the orbits to be that far from each other, and then that was not correct. Anyways, it turns out by Kepler that they found out that the planets were revolving around ellipses as their orbits. So we got the largest and nearest distance, it looks like. Let's try metric. Yeah, let's go with the metric system. So the eccentricity is 0.0167, and we have the largest and shortest distance. So we have those pieces of information that was needed. Oh, and the orbital period is 365.25, so it's like a quarter, right? 365 and 1/4, and that's why every 4 years they have to add on a day. But then you know that there's also this 0.00636 days, which every so often somebody, I don't know, a group of people, they have to account for a leap second and add that on to the time. Do you guys know about that? You should Google it, something about leap seconds. And there's a group of people that decide this, and there's supposed to be a leap second added on, like this past June or July or something. I don't know if it ever happened. Anyways, that's why they have leap years, is because of this calculation over here. All right, so we have the largest distance. Which one's the largest distance? The Aperion, or is, I don't know. Let's go 1.52. And the peri is 1.47. So if we add them together and divide by 2, we're going to get A, right? So we add this together, ap plus peri, and then divide by 2 equals A. So A is equal to, they have the same 10 to the 8th. So when we add them, you guys know how to add, like, what do you call these? Scientific notation, right? So this is 2.99. So that's your A divided by 2. And then, and then your E is equal to this. So that's it. And then if we were to graph this, or not graph it, but put it all together into our function, our polar coordinate ellipse that models the Earth is going to be, what was it again? A times 1 minus e squared. So A, we got 2.99. Suppose we can divide by 2. So that's your A, and then 1 minus 0.0167 divided by, and then they're just assuming that this is going to open on the right side, right? It's almost circular, but times cosine theta. Oh, yeah. Right here, right? Just here, or the, yeah. So that's it. That should model our path of the Earth. Okay? Any questions? Okay. So let's move on to chapter 12. Let me just put a few more marks here. Okay, so everything that we've done so far may have been a review. I think it's covered in some pre-calculus courses, but not necessarily all of them. But we've done things like the conic sections. I'm hoping you're kind of familiar with already, and then so the probably maybe the new things might have been just polar coordinate stuff. So this is kind of like a taste of the new stuff that we're going to get into. And when they talk about multivariable calculus, this is now when we start expanding ourselves to beyond 2 dimensions. And so chapter 12 is going to introduce us to 3-dimensional visualization and geometry analysis and stuff like that. So let's get into chapter 12. Oops. All right, so our task is to try to visualize things that are happening in a 3-dimensional coordinate system, and then introduce ourselves to a few simple graphs of things. And they're going to be introduced as a set of points that satisfy this equation or something like that. So the idea here is to get used to drawing things in 3D, starting with the X, Y, Z axis. And then we're going to identify some simple planes and axes, and then we're going to find distances between points and some stuff that if you've already gotten a start on your labs, which are due, should have been due before class, but it'll be due tonight at 11:59. So if you've taken a look at that, you kind of know more or less what to expect here. So let's start with drawing a 3-dimensional set of axes. And the idea is to look at them from a point of view that's easiest to look at. And I would draw this 3 lines or 3 vectors or 3 arrows coming from the center point, which will be labeled as the origin, and then the axis will each be labeled with an X, Y, Z. Now, the X-axis, the Y-axis, and the Z-axis have to go in a specific order, And so when we label it, we have to make sure that we're labeling it correctly. If we mislabel one of them, then things are going to switch. So in general, we think about this line as a line going towards us, if you can try to imagine that, as the x-axis. And then the line that's kind of going to the right is your y-axis. And we think about the z as going up and down. Now, for those people who have taken some physics and know about the right-hand rule, the idea of this order is important because of the right-hand rule. And the idea is that your x is labeled first, and then the y, and then the z. And the idea there is that if you put x and y in that order, if you wrap your right hand, your fingers of your right hand around the x and y axis, then the direction that your thumb is going to be the direction your z is going to go. Okay? If you do that with your left hand, it's not going to work. So this is the right hand rule. Can you guys imagine that? If you want, take 3 pencils, and identify which one's the x, which one's the y, and which one's the z. And then if you identify, for example, as this red, or the blue is my x, and my red is my y, and then I'm going to wrap my right fingers around the blue first, because that's the x, and then the red, the y, then my z is going to have to go straight up. Okay. If I wrap my fingers around the red first, which is the y, and then the x, then my thumb's going to go down. So we'll get more into the right-hand rule later on, but that's a general idea for your set of axes, your x, y, z axis that defines your three-dimensional space. Okay? So, any questions about that? So sometimes we might if you look at it from another point of view, we might have this looking like this, and this is actually should be 90 degrees. And so we can label this as your x and then your y, and then your z still goes up and down if it's still going in that same order. So that's just a slightly different point of view of our three-dimensional set of axes. Okay? So that means
Another way to think of it is that if you're looking at an XY graph in the XY plane, Z points away from you other than Z.
towards you.
Yeah, if you grab Z and hold it down. Oh, right, yeah, okay.
Yeah, so it'd be, if you were to look at it from the top,
Now I see. Okay.
if you're looking at it from the top, like that, then the Z would be pointing towards you. Okay? And that's another viewpoint that we're going to be interested in looking at. So we're going to be interested in looking at things from different viewpoints so that we can get an idea of how things are visualized. Right? There's a class in, I don't know what department it is, I think maybe in multimedia. It's called 3D graphic visualization. And I've always thought that that would be a good class. Didn't really want to make it as a prerequisite for this class, but it would be a good class to have before coming to this class try to be able to visualize a lot of things in 3D. But with the help of computers and stuff, there's a lot of these things that we can, if you can't visualize it off the top of your head, we can always put it up on the computer and screen, and then you can see it. Okay, so this is the idea, or this is the beginning of the setup. Let's get into some of the things that we need, and like some of the basic equations that we'll need to describe the elementary parts of our three-dimensional world. And I'll start by going back to 2D. So in 2 dimensions, we have the x, y. We label it x, y, but you can really label it whatever you want. But we'll call it x and y. And then if I wanted to express the x-axis as a relationship between the variables x and y, how would you label the x-axis? Y equals 0. Right? And then, likewise, the y-axis is x equals 0. Okay, let me expand this a little bit. You guys taking notes in pencil? When I say, or when you say y is equal to 0, it's a relationship between an x and y value that says that your y is equal to 0, and what does it say about your x? Yeah, well, all of those. It doesn't matter what x is, y is always going to be 0. And if you throw out an x value, like x is equal to 5, y is going to have to be equal to 0. If x is equal to 7, y is going to be equal to 0. If x equals 3, y is going to be equal to 0. So you're always going to be on that y-axis, right? So when it says y equals 0, it doesn't matter what x is. And because x is not part of this equation, in that relation, it doesn't matter what x is equal to, your y is always going to be equal to 0. Okay? So that idea, when a variable is missing, that idea just means you can let the missing variable, whatever it wants to be, then you're going to continue to have whatever equation you have, which is y equals 0. Now let's think about that. Let's go to 3D. So if I give you an equation z is equal to 0, I want to be able to describe all the points where z is equal to 0. And like in the two-dimensional example, it doesn't matter what x is, or in this case, it doesn't matter what x and y are equal to. It doesn't matter what x and y is equal to, z is always going to be 0. I didn't talk about points. Oh, I forgot to talk about points. You guys know how points work in 3D, right? Just x, y, z. So I guess before we do that, let's talk about points. So when you describe points in 3 dimensions, you're, of course, looking at 3 numbers, an x and a y and a z, and that would be described as a triple. And when you do this in Cartesian coordinates, you're basically going to walk along the x-axis, then along the y-axis, and then along the z-axis. So let's pick a point, like, for example, 1, 2, 3. If you were going to pick a point 1, 2, 3 and try to graph that in 3 dimensions, you would move 1 unit to the 1 unit in the x direction. Now, I'm going to put a little tick mark here, but I'm going to make my tick mark just to make it like visually, what? I was going to say appealing, but it's actually more important than that. It's not just to appeal to your sight, but it's also to appeal to the geometry of it. I'm going to draw a tick mark that's parallel to the y-axis. And that actually shows perpendicularity. That tick mark is actually perpendicular, although if you look at it, it doesn't look perpendicular, right? But technically, because of the viewpoint, it actually is perpendicular. And then I'm going to move 2 units along the x-axis. And the way to do that is to, you could draw the whole thing, but you can make a little box. Now this is a 2-dimensional rectangle. It's not a parallelogram. I mean, it looks like a parallelogram from our point of view, but you have to look at it from the viewpoint again, a 3-dimensional viewpoint. It actually is a box, a rectangle with right angles. And then you're going to go 3 units up, the z, 1, 2, 3. And the thing to do is maybe to measure this distance that you moved over here, and then that same length of measurement would go where you left off. So it's not as high as those 3 tick marks that you put on the z-axis when you're drawing it. And what you get is this point 1, 2, 3. And each point can be drawn as, you know how we have that box down in the bottom, we can also think about this as a box along the x, box along the y, box along the x and z, box along the y and z. And then all of a sudden you get this cube-looking thing, and that's and that cube will have the measurements of 1 unit along the x, 2 units along the y, and 3 units along the z, as per your point. Okay, so that's how points work in 3 dimensions. And if you go negative, then you just go the opposite of the positive direction of where the line's pointing, so you just go in the opposite way. All right, now that we know a little bit about points, let's go back to this idea of trying to figure out the set of points x, y, and z where z is equal to 0 and x and y don't matter. It's the what? What plane? The xy plane. So if we draw this, we can say z is equal to 0, right? It doesn't matter what x is, so let's say x is equal to 0, y is equal to 0, then z is equal to 0. Let's say x is equal to 1, y is equal to 0, then z is equal to 0. Let's say x is equal to 0, y is equal to 1, and z is equal to 0. And it turns out that it doesn't matter what x and y are equal to, your z value is always going to be 0, and that is going to, well, the way I'm drawing this right now, it's just a little rectangle on a plane, but if you imagine this going infinitely in all directions, then it would be the whole xy plane. So this z is equal to 0 is exactly what the xy plane would look like. So in fact, a probably slightly better drawing of this might be to draw a generic rectangle on the xy plane and just say, imagine that's going to go on forever. So similarly, we have, when z is equal to 0, we have the xy plane. If you imagine when x is equal to 0, what do you think we have? You have the yz plane, right? So if we could draw that. This is my x, my y, my z, a yz plane. I would probably draw these points to say this is where they intersect, and then maybe that might be good enough to try to visualize that. And then your y is equal to 0 would be the other one. What's the other one? XZ plane. Sometimes I like to just say ZX plane to be consistent with the right-hand rule. Think about it. X, Z, positive y. So the XZ plane comes in a little bit more of a slant. Okay? So these are the coordinate planes. The coordinate planes can be described with some variable equal to 0. Right? And when I say coordinate planes, I mean either the xy plane, the yz plane, or the zx plane. Those are equivalent to like the axes or something, the lines that describe the axes in 2 dimensions. So now let's get away from 0 and throw some constants and see what happens. What if I had like z is equal to 1 or 2 or 3? What do you think this is going to be? Any ideas? It's the xy plane, but shifted up or down, depending if it's positive or negative. Right? So we start with z is equal to 0. z is equal to 1 would be the same plane, except it got shifted up by 1. We can have the negative planes down as well. Z is equal to negative 1 would be the same plane shifted down 1. Okay? So we got those shifts figured out. And likewise for x is equal to 3 and y is equal to 7 and all those other examples. If they're equal to a constant, they just got shifted. All right? That wasn't too bad, was it? Now let's get a little crazy here, a little bit. So I made a comment about the variables missing, that it doesn't matter what that variable is. The variables that are there will still be able to represent that. Right? So let's say in 3D, I have x squared plus y squared is equal to 1. Now, we know that in 2 dimensions, on the xy plane, x squared plus y squared is equal to 1 looks like a circle, right? But if I were to say I have this equation, x squared plus y squared in 3 dimensions, what do you think this is going to look like? Cylinder. Well, it's not filled in, so I don't think it'll be a disk. So remember this drawing? If it's towards you. Think about looking at the circle like that. And that equation didn't have a z in it, right? So we said if it didn't have a z in it, z can be anything, and then I'm still going to have an x squared plus y squared is equal to 1. So when z is equal to 0, x squared plus y squared is equal to 1. That looks like a circle. Now, if I go up when z is equal to 1, that's on this plane, right? I'm on this plane. I'm still going to have x squared plus y squared is equal to 1. And when z is equal to negative 1, that's this other plane. It's still going to be x squared plus y squared is equal to negative 1. Or it's equal to 1. So imagine the circle going up along the z and going down along the z. So what do you get? Somebody said it already. It's a cylinder. So this is actually a cylinder. So in 3D, you can imagine drawing this circle in 2D, and your circle isn't quite going to look like a circle because it's with perspective, right? You're looking at it at an angle. And then you're going to have the same circles up and down. Has to be the same circle. Oops, sorry. It's a hollow cylinder. Should be hollow. What would make it not hollow? You can fill it in. What? No, you would say x squared plus y squared is less than or equal to 1. And now it gets filled in. Because now this is a disk. Right? And then if this is your equation or your inequality now, I guess in this case, and then you put it in 3D, then it would be a solid. But without the less than signs, if it's just equals, then we're always going to be looking at surfaces. And surfaces could be closed surface, but it's still not going to be filled in unless we force it to be filled in with something. So if I had z is equal to y squared, and I'd say this is a graph in 3 dimensions, what should this graph look like? Let's start with the variables that are there and draw it on the axis that it exists in. Kind of, yeah.
Take that equation and extrude it along the x-axis.
Extrude. That's a SolidWorks thing, isn't it? Extrude.
It's also how they make pasta. By pushing the material through a pattern form so that it comes out a cross section of that.
This is your z is equal to y squared parabola, and move it along the x-axis. And then when you draw it out, you probably want to make sure that you take into consideration the visualization of things, like what gets shaded, because there's going to be some things that are behind something. And then you have kind of like a trough with no sides, or just your piece of paper. Okay? Yeah. Well, I kind of, as I was making this, I see the back end of this trough over here, and I know that now because of the way this is being drawn, this part over here is behind another surface, or the same surface is behind something. So I probably wouldn't want to trace this part in, so I'll take that out, and then now I just would be tracing out this part, and then it would stop over here, for example. It just depends on how you view things. Yeah, as long as you could kind of draw from any perspective. Yeah. Right. Yeah. Well, I don't know. The drawing, I'd like for you guys to be able to draw these things, but I'm not going to expect you to be artists. But I think some of the basics would be good, even if you don't exclude the things that are behind, that kind of viewing, then that probably wouldn't be that big of a deal. but I would expect you to be able to draw some things in 3 dimensions. Yeah. Uh-huh. Okay, well, practice. Let's see how it turns out. Yeah, I thought about taking a drawing class and to try to be able to teach a drawing class, but I just kind of dabble. All right, let's try something else. Let's try another graph of something that would be kind of interesting for us. Might be interesting. So let's try x plus 2y plus 3z equal to, now let's see, let's try 6. Try to make it look like it'll have nice numbers. So I want to try to draw this graph, or maybe a piece of this graph. Yeah. This is a relationship between x, y, and z, so I need to find out the points that would satisfy this particular equation. So in pre-calculus or even algebra, when we start trying to find equations or trying to plot graphs of things, one of the things that we try to do is we try to figure out where it hits the xy plane, or not pre-calculus, where it hits the x-axis or where it hits the y-axis. So that might be a good thing to start with. Let's start with the idea of where this is going to hit my x-axis. Now, if I want to figure out where this is going to cross the x-axis, I'm looking for a point somewhere here along the x-axis. What can you say about the y and the z of this?
0.
So if y is equal to 0 and z is equal to 0, it looks like I should be up along my x-axis, right? So let's set y equal to 0 and z is equal to 0. And if I do that, x is equal to 6. So at 6, that would be more specifically 6, 0, 0, because x and y are equal to 0. I would be that point. And so that point exists in this graph. All right? Let's play the same game with the others. Y-axis at y is equal to, by setting x and z equal to 0 this time, x and z equal to 0, y is equal to 3. That's what I got. So I'm here at 0, 3, 0 as another point on this. And then let's take that last one, z-axis at z equals to 2. So I have that. Okay? And now, there's one more thing to note about an equation that looks like this. You know what's special about this equation? What kind of graph that this would give? Why? Yeah. It's a plane because it's all to the first power. So if it's a plane, then all its intersections with other planes would be lines. And we'll learn a little bit more about that later on. But more specifically, if we take a look at this graph, not just at the axes, at the x, the y, or the z axis, but actually on the xy plane, not at, let's say on the xy plane. Now, what was the xy plane again? Z is equal to 0, right? So the xy plane is when z is equal to 0. So if I want to see this on the xy plane, I would set z is equal to 0. And I would have x plus 2y is equal to 6. Now, if I graph that, x plus 2y is equal to 6, I don't know, slope. Y-intercept is 3 and slope is 1/2. Is that right? Y-intercept is 3 and the slope is 1/2. So this will hit here at 6. Right? So we actually see this line right here. Equivalent to this line. And without doing the other sides, the rest of them will just kind of follow. So this is a piece of the plane. Well, if we cut it off, yeah, then it would be a tetrahedron. What's a tetrahedron? You guys know what a tetrahedron is? What? It's a four-sided polyhedron. It's four-sided polyhedron.
And a polyhedron is a shape with flat sides.
Shape with flat sides.
A shape composed of polygons.
Shape composed of polygons with flat sides.
In 3 dimensions.
In 3 dimensions. Oh, that kind of brings back the Platonic solid ideas. Do you guys know what Platonic solids are? They're called regular polygons because they're made with exact same size of a polygon that are made into a polyhedron. And there's only 5 of them. There's only 5 Platonic solids. There's only 5 polyhedra that all have the same sides. Okay? You guys know what they are? Tetrahedron, 4-sided one. The next one is the cube. You know what a cube is. Some people call that a hexahedron because it has 6 sides. Octahedron, 8 sides, all triangles. The cube, by the way, is squares, right? Tetrahedron would be triangles. So octahedron is 8 triangles. You guys know what the 4th one is? Dungeons and Dragons. Dodecahedron, 12 sides full of pentagons, regular pentagons. And then the last big one is the... Nobody plays Dungeons and Dragons anymore? Icosahedron. 20 side full of equilateral triangles. I have them in my office. Maybe I'll bring it one of these days. Yeah, so if you look at before Kepler came about, and I think it might have been, Aristotle or way back in the Greeks, they tried to imagine going on a tangent here. They're trying to imagine the orbits of the planets, and they're trying to find the distances from the planets, and they're imagining that the platonic solids were the ones that are making these rules. That would be an icosahedron. That's 20-sided die.
Why would the platonic solids make those rules?
Because it seems so heavenly, and that's what
So
they came up with.
effectively because it's better shot at space.
Platonic solids is named after Plato, by the way, the Greek philosopher. Those Greek philosophers, they kind of had this mathematical logic behind them. Nah, he wasn't pretty. All right, so the last thing I wanted to show you was the distance formula in 3 dimensions, which is really an extension of a distance formula in 2 dimensions. And I think I just have that in my notes, so I'm just going to copy it. Got this. So let me put these last 2 formulas down, which mimic the distance formula in 2D, and then kind of extends that distance formula into a sphere, because if you take a look at a sphere, let's say you have a point, x naught, y naught, z naught, just a point in space, and then you give a fixed distance. Say the fixed distance was r distance away, and any point, all the points with that fixed distance away from that fixed point, x naught, y naught, z naught, if you put all those points together, you're going to make up a sphere. Does that make sense? If you yeah, I don't know. Get a sphere. If you take you go burning a stick in the campfire in the dark, and then your stick is glowing, and then you hold your hand in one place, and then you spin it around in many different directions, right? If you spin it fast enough and it's dark, right, so all you see is the remnants of light, you could actually almost see a piece of a sphere when you do that. Do that next time you go camping, or tonight. All right, so if you had a hard time viewing this, I think I would recommend a graphing program that would allow you to imagine how these graphs look like. Starting off with the coordinate planes. And then let's throw in a cylinder, x squared plus y squared, right? That's all it was. Or x squared plus y squared is equal to 1. That's all it was, and you get a cylinder. That trough, folded paper, right? And then that last one we just did, x plus 2y plus 3z equals 6. That one's a little hard to see, so if we kind of zoom in a little bit, zoom out a little bit, and maybe take out some of this noise. Let's take out the trough, let's take out the sphere, or the cylinder, and then let's just take a look and stop it at the front. Maybe back up a little bit more. If we take a look at this little piece over here, that's like that little triangle that we drew, the tetrahedron. If you enclose it with the sides and then the bottom, then you have a 4-sided tetrahedron. And then, of course, a sphere. Well, you would know how the sphere would look like. Okay, So all these can be viewed, visualized. We can definitely draw it on a program like this, but my challenge to you is to try to draw these things by hand and make it look like it's coming out of your page. I think that would be advantageous. If you can't do it, then that's fine. You could just try to imagine it. And if you can't imagine it, then get a graphing program like this. Speaking of graphing programs, I will post, speaking of posting, I have included, I don't know if this is the best way, somebody suggested about a place to put notes. So I've included in the discussion here, note sharing discussion board. I don't know if this is the best place to put it, but for now I'll leave it there. Note sharing discussion board where you can post things that you want to post. If you want to post notes, if you want to post ideas, but keep it class related. You know, I don't want to hear about somebody's weekend on this post. And on this post, I will start it by giving you a link to a program that you can use for free that allows you to visualize three-dimensional things. All right? Okay, that's it for now. See you guys on whenever. Tomorrow.